Hello everyone, welcome to this stream. Today we will continue work on the Icebreaker bitsy that we assembled in the last stream. I wanted to test it, bring it up, and make sure that the bootloader works. The story becomes quite complicated and interesting actually because I spent yesterday trying to get the bootloader running. Now the bootloader is working, just FYI, that's spoilers. But there was quite an interesting journey to get there, and I would like to share that with you and basically do a little bit of storytelling. And then maybe we can program on it, because I have to see how the DFU bootloader works myself. So that will be interesting. I will be learning something live on stream, which does happen here from time to time, but it's usually not planned. This time I know that what I'm facing. So yeah, exactly. Yeah, stay at home and work on FPGA projects. That's a great idea. That's what we are doing here. So we have the desktop here. So let me show you what we are working with. Really quick, a recap. So as you know, this is the Icebreaker Icebreaker. Icebreaker is an ICE40 FPGA development board for beginners, as well as an evaluation board for your projects if you're building something new. Also, more and more people are using it as a reference design, which is very nice, because you can find the schematics and files online, so you can take it and modify it to match your needs and make your own project, or take this as a dev board, attach whatever hardware you need, make a prototype, test it, make sure everything works, and then boil it down to your own board. The Icebreaker itself has these PMODs as connections. It has all the pins broken out. Unlike other dev boards, it was important for us to pretty much offer all the pins within reason as available outside for your own projects. The problem with other dev boards that you see from, for example, from DigiLand or from manufacturers, usually they put a bunch of different peripherals onto the board that you cannot remove, and you cannot use these GPIO for anything else but these dedicated peripherals. So you have like 7-segment displays on there, and it's like, okay, great, but for my project I don't need that. I need those pins for something else. And so then the saga of removing components starts. So for us, it was important to design it so that you have jumpers. There's, I think, maybe one pin that is not fully available on any pad easily. But in general, everything should be available on here. So that's the design goal here. Same thing with the bitsy, which is the smaller version of this. So that's Icebreaker bitsy, which is a boiled down smaller version of this. The big difference between the bitsy and the Icebreaker is that the Icebreaker has an FTDI, 2-channel FTDI chip on here, which is used for programming of the flash that contains the bit stream for the FPGA. And it has, the second one is connected with UART pin, so you can get serial out of your FPGA with the second port on the USB interface. And then on the back we have also jumpers to put it in FIFO mode. That is not super useful because it's the secondary one. It's details, like technical details. We usually use, for high-speed communication to the FPGA, we actually reuse the SPI lines that are used for the flash chip. When the FPGA starts up, it pulls out its configuration out of the flash, and then if the FPGA doesn't need those pins, you can continue using them from the outside, from the PC, to talk to the FPGA. For that, we have a chip select line, an auxiliary chip select line, which is this jumper here on the back, which is by default connected. You can then do chip select with the FTDI and talk using the MPSSE engine, which is the multi-purpose serial something engine from FTDI, to stream SPI at up to 60 megahertz, I think. No, was that right? Maybe it was 30 megahertz, but it's still fairly quick. We can get data into and out of the FPGA in synchronous mode. And that is about maybe half of the speed of the very large pin count parallel interface, which is the asynchronous or synchronous, I think it's synchronous parallel bus, which is only on the second port. It doesn't have a synchronous mode on the second port, only on the first port on the DI chip. It's a limitation of it. Yeah, it's async, thank you. So the synchronous mode, which is faster, like really fast, you can saturate the USB high speed with it, is only available on the first FTDI port, which is not connected to the FPGA because it is used for programming. So, anyways, design decision where you have trade-offs that you have to live with. Yeah. Pesmerk4, thank you for the follow. Welcome to the stream. All right, so that's the story here, and the smaller board does not have the FTDI chip on here. So the FTDI chip, as you might know or might not know, is actually twice as expensive as the FPGA on this board. So at least in purchase for me. So FTDI, I tried to contact them. I asked them for reasonable prices for a project. They said, screw you, go away, we don't care, buy it from DigiKey at full price. Unless you want to buy 10,000 of those chips, which is ridiculous amount of chips. So FTDI doesn't like its customers and doesn't want us to have good development boards. So that's the current problem with FTDI. So I'm, as you might hear, not a huge fan of the FTDI because of these reasons. But because of compatibility, we still are stuck with FTDI because a lot of software supports it. The vendor tools that we want to be backwards compatible with are using FTDI as their default programming interface. So that's again a reason why we keep the FTDI chip on here. Although the board is designed to be used with open source FPGA development tools, which in my opinion are easier and nicer to use anyways. So if you think you will get faster going with the vendor tools, you just try the open source tools. It will go faster. You will get up to speed faster. It's easier to install. Just forgo the vendor tools if you can, and just use the open source tools. If you have some requirement, there are some reasons to use the vendor tools in some specific cases. It's like there are some specific cases where the optimization works a little bit better, I think, still with the vendor tools, but these are very corner cases. Or you need to or you want to compare the results between one and the other. But this was important for us to still support the vendor tools because of that, so that you have the option. So anyways, the bitsy doesn't have the FTDI chip on it, so we had to come up with some other solution. So as I already told you in some other streams, the history of this is it started with the Teensy. Teensy is Paul's, who is here in the chat, an Arduino board that uses an ARM Cortex M3 or M4, depending on the version. It's a really nice board, really recommend that if you want a good working Arduino with really good libraries, because Paul is really good at making the libraries work efficiently and well. Get a Teensy. It's like you will do yourself a favor using his libraries for the Arduino. So if you are into Arduino stuff. But this is a nice form factor that I really like. And so based on that, I made the bitsy, which is a board. Where is it? It's a board for testing Blackmagic Probe. And then Luke Valente made Tiny FPGA, which is exactly pin compatible with the Teensy. And then I made the Icebreaker bitsy, which is also similar has this is something we will address in the next revision to make it a little bit more, hopefully, pin compatible with the Teensy, so that you can use the same hardware that was designed for the Teensy, hopefully, or Shields. So that's that. Yeah, and the problem we had was the bootloader for the tiny FPGA, which worked on the Ice40 LP, had issues running on the Ice40 up5K. So this is a chip that obviously was designed for some specific customer of Lattice. Move the camera here. It was designed to have as low power consumption at static power consumption as possible. So to achieve that, the interconnect on this chip especially is significantly slower than on other Ice40 chips. But as an exchange for that, you get a few really cool features, like a lot of block RAM compared to the LUT count on the chip. You have 128 kilobytes, right? kilobytes. Sylvain will correct me there, of memory. I should pull up the specs, but it's pretty nice. You can put a lot of stuff. For example, you run out of LUTs on this, you can put stuff in RAM, for example, to execute from there, to have a state machine, or have a frame buffer for driving displays, and. So it is a pretty cool chip. Yeah, 128 kilobytes, so that's correct. Okay, good. Yeah, I always question if I have the unit right. So yeah, this is a lot of memory for a small FPGA with just 5,000 LUTs like this one. It's still quite a significant amount of LUTs. You can put a RISC-V microcontroller on here. And so Sylvain, as well as some others, Sean Cross for the FOMO, which is this guy, which is like a USB port. This is also an up5K FPGA on here, which is plugs into a USB port. This is basically a USB plug. It has like 2 touch buttons and RGB LED, and can be plugged into USB. This is very cool, and they got the bootloader working on this. But Sylvain made a new revision, a better bootloader, which I managed to get, or he got working on the Icebreaker, and his like updated version of the bitsy, which is this one. And it essentially presents itself as a DFU device, which you can then program with your bitstream. So how this works, we will discuss it. I will show you on the monitor a little bit the breakdown of how the structure of the memory on the flash is, and then we will know how this bootloader works. So you do sacrifice some flexibility and some memory on the flash in exchange for not using the FTDI chip, having a cheaper board, a simpler board. So it is quite a trade-off. And it is only USB full speed instead of high speed, which you get with the FTDI chip. But it's, as always with any engineering, there's always trade-offs that you have to handle. Arduino? Yeah, I don't even know what Arduino is, to be honest. Maybe Arduino is the footprint. Oh, the Arduino? Yeah, it's on purpose not on here because it's a terrible board. Yeah, so Arduino is very, very cheap. It is also in the same small form factor, and it has, but it's like, I'm not recommending it to anyone. It is a terribly designed board. It has very bad decoupling. It's not. I try to use it as a reference. It's like do not use it as a reference for the board, because how the power supply is built. It is so especially the first revision had a lot of problems. People had to take the boards and add capacitors to have enough decoupling so that this thing was starting up at all. The second revision of the Arduino is better, but still bad. It's like you have voltage regulator on one side of the board and decoupling capacitors of the other side of the board. It's like, I don't know how that happened and who signed off on this, especially considering that it is listed on the Lattice website for sale. So if the person that designed it is in here in the chat, I really apologize, but I'm sorry, this is not a very well designed board. All right. It is cheap though, which is nice, but I assume it is because either the person is not making any money on these boards or Lattice is giving them the chips for free. Yeah, I'm not that lucky with my boards, but I try to share the best practices, how to design boards. They are open source, so people look at them and want to be able to copy the design and build something on top of that. So it is good. As George Locamides every time manages to find something that I'm doing wrong. So I always, it's like, I get like, George, this doesn't matter. And George is like, well, be careful. This is something people will see and use as a reference. And so good practices prevail. And he's right. I know. You get just defensive of your own design sometimes, which is understandable. It's your baby, right? Ah, yeah, Karen, welcome. Welcome to the stream. All right. All righty. So, we should look at how this is structured. So, and as I said, this stream will be probably a little bit more disjointed than usual. But essentially what I ended up doing, let me look maybe at the desktop here. So this is the bitsy, and what I did is I managed, maybe we should just plug it in and show you how it works. Follow? Devo is following. Thank you very much for the follow and welcome to the stream. So yeah, how do we approach this? So the cool thing is, this, if I plug this in over USB, let's see. Maybe let's do dmess. Let's see if my dmessage is not being spammed with stuff. All right, so I did manage to get that bootloader running. So the bootloader that Sylvain put together is consisting of several parts. But essentially what it does is when I plug it in here, oh, right, I have to hold the button, right. So when I hold the button, the user button, and plug it in into USB, it will appear. So you get a full speed USB device with the Icebreaker bitsy using manufacturer is Osmocom, which is cool. And the serial number is I think he pulls it out of the flash chip. There is a serial number in the flash chips themselves. So something we have to explain is how the structure of this looks like. So let me open KiCad really quick. So so Icebreaker bitsy. Maybe we can look at the schematic. So this is the FPGA, and the FPGA is essentially just a volatile memory. And with caveats. It's like this, everything has asterisks attached, but let me just oversimplify. The FPGA itself, in the mode that we are using it in, it basically is empty. It uses its hard IP SPI interface to read out of this flash chip from address 0, or there is some config bits in the beginnings, but it like reads out from address 0 information, and then it configures all its lookup tables and sets up the FPGA to behave the way you want. So if you don't know how FPGAs work, it essentially a microcontroller, for example, it would be reading an instruction at a time and executing those instructions, and then maybe jumping in memory to read out different things. An FPGA holds that is basically a fabric, like an array of lookup tables that are connected with interconnects together. Which is, you have the I/O pins that are inputs that are connected to interconnects and latches, and this is connected to lookup tables to implement logic that then is connected to other outputs to create like input-output device. Again, I'm oversimplifying, but that's practically what it is. But those lookup tables and those latches, they're configured like a volatile RAM. They are using that technology of volatile RAM to configure itself. And so you need to load it into it, because when you power it off, it will lose its configuration. So the flash chip contains that bit stream, that's the technical term. It's a bit stream that configures the chip. I would explain it like it does all the code lines parallel. Yeah, so essentially, but it's like a big configuration of all the logic. So all the logic is there, and it reacts based on the input. So clock is also an input. It like clocks everything, and based on that, you can have those latches pull in data and move it along. And everything that goes in goes out, and you can have multiple paths of logic going in parallel to each other. So that's the physical representation of what is going on in there. That's why writing Verilog is, or any HDL is so much different from programming, because you are not writing sequential things to execute, and you have to go out of your way of creating another parallel path by spawning a process or running it on a separate CPU. That's like, you have to put work into making something in parallel. In FPGA, everything is in parallel in the first place, and you have to work to synchronize it and make it not go in parallel, but actually happens in a sequence. So it's a very different mental approach how you design this stuff. So for me, the hard part about designing Verilog is there's so many things happening at the same time with each cycle of a clock that it becomes sometimes difficult to keep it in your head. So then we have that FPGA that is loading its configuration from the flash chip. So that's step one. Second is, how do we get the flash chip configured? We don't have an FTDI chip. So on this board, I do have this plugged in, which is an FTDI board to program the flash chip separately while the FPGA is disabled. But this is not the intended way of using it. You want to use the USB interface. But there is no USB hardware here. The FPGA itself has to implement a USB interface. So what happens is, we have a configuration in this flash chip. Let's see, there is a very good breakdown. So you can have multiple configurations of the FPGA in the flash chip. They are basically in multiple sections, one after another. And there is a special piece of hardware inside the FPGA that you can actively configure and say, please restart yourself and load a new configuration from a different part of the flash in a later section. So what Sylvain did is like he has a small bit in the beginning that only does sets up things, loads and jumps to an application, which the application itself is implementing USB using a RISC-V microcontroller and some custom hardware that is attached to that microcontroller. And with that USB device that he implements in the FPGA itself, with that you can then use USB to flash the flash chip in a third section even later, and then restart again into that thing. So it is like a three-step process here if we are programming it. So when we are holding the button, we can force it to go into the bootloader. So the important detail here is this really first stub doesn't have USB implemented, but it looks if there is a valid bit stream and jumps to it that we programmed as a user, our user bit stream. There is, if you hold the button, it's hardware bootstrap. It's like a bootloader, like a bootstrap bootloader on a microcontroller. Same thing, same idea, but applied to FPGA. So we have basically a firmware, which is bitstream configuration of the FPGA that implements the USB. No, it reconfigures itself on the fly. That's exactly the point. So this is the cool thing about this FPGA part. So some people will say it's like, oh, is that partial reconfiguration? No, it's not. That's a different concept. So Xilinx FPGAs are known for its partial reconfiguration capability. So it means it can reconfigure parts of the FPGA on the fly. This is not what we are talking about here. We reconfigure the complete FPGA. So we start up in this very simple bootloader that doesn't do much. It just looks, it's like, oh, is there valid bitstream here? Oh, I will just jump to it. This is the application of the user. Okay, good. Or, oh, is the button held down? Oh, then I will jump to the bootloader that allows us to flash the firmware, that implements USB and allows us to flash the flash chip, and then we can restart into the user application. So there are multiple paths to get to it. Yes, Sylvain describes. Yeah, so I hope that is useful. All right, so the logic is hard-coded. So the logic is hard-coded per se. We do build a bit stream and we do flash it, but we can tell the FPGA to reset itself and load a new configuration from a different place in flash. That's all that's happening. So static as in it is in the flash a static bit stream that cannot change itself, but we can load a new one. So a completely crazy idea, something that might be possible, is essentially take a bit stream, twiddle a few bits, write a new one in the flash, like do like partial or reconfiguration by changing bits, putting it in a new section, and then starting that new section up. That might be a crazy thing you could do. Yes, the logic that reads the bit streams is a static thing. This is part of yes, so this is a so-called hard IP. The hard IP, it's called wormboot. It's a block inside the FPGA, which is a hard, unchangeable machine that has nothing to do with the fabric itself. That sits to the side, that can be configured. It has like a register, and you can say, it's like, please, this is the address you want to load it from, and now go. Yeah, there are some mixtures, but this is no. So again, so there is no microcontroller on this thing. There's no such thing in the mix on the Icebreaker bitsy. There's only the FPGA, and it has a static machine that is not a microcontroller, cannot be programmed, that is basically a state machine that can do a thing. And that state machine can load a new bit stream from a different place. But we can put a bit stream inside the FPGA that emulates or implements a microcontroller. That's the RISC-V microcontroller. We can configure the FPGA to become a microcontroller, essentially. So that's why FPGAs are used a lot for prototyping and developing new chips. You use them as reconfigurable platforms and test beds to test your new CPUs, new architectures, new hardware that you then later convert into hard silicon. It is all Verilog, and I didn't write it. It was Sylvain or TNT. He is in here, Sylvain Smanout. He wrote the bootloader. It is partially written in Verilog, partially written in C for the RISC-V microcontroller. So the USB part is not fully just gateware implemented. It's not just hardware. There is some hardware and a little bit of a state machine, as far as I understand, plus a microcontroller that runs the whole show and does more high-level stack-related stuff for the USB stack. So that's how it is implemented. But anyway, so now that we know that we have this flash chip, we have the FPGA, how it configures and how it self-reconfigures itself and self-reprograms itself, we can look at the actual implementation. So as you see, it comes up as a DFU, but essentially, Sylvain gave me a link. Okay, so Sylvain explains it in more detail. This is pretty much the same split you would find on a USB-enabled microcontroller. Hardware, so the gateware, handles transaction level, and the higher level of the stack is implemented in software. So that is implemented in C, running on the RISC-V microcontroller, and then there is a low-level hardware part attached to that microcontroller, and that's the configuration of the FPGA. So Sylvain, you gave me a place where you had the breakdown of the flash structure, and I don't remember where this was. Should have opened it. Let's see, this was in the Icebreaker Discord channel. MK multiboot, that's where it was. It's in the Python script. So all this stuff, all this complete implementation, you can find here. Ice40 Playground. So this is Sylvain's playground for Ice40 projects, and there are two projects in here. There is a boot stub. This is the first level bootloader that doesn't do anything besides, I think, looking if the button is pressed and starting either the USB bootloader or starting the application, as far as I understand. And the second one is the RISC-V USB, which runs as one of the two possible applications. So either this or you have the user application, and this would be the other bit stream. And this is also split in two halves. You have the RTL, which is the hardware, which is the FPGA configuration. It's written in Verilog. And you have firmware, which is written in C, which implements the USB stack. So this is how it splits apart into the two parts. So this is what you would use on a normal microcontroller, and this is the hardware itself, so the configuration of the FPGA. So let me see. I will get to your question, Reset Public, in a second and tell you what I think is the advantage versus disadvantage. Because this is an interesting discussion. So utilities, and there's the MK multiboot. So let's look at that. So here we go. This is how the flash is split apart. So there is a multiboot header, which contains information about what different multiboot sections are. And this is this hard IP engine, the warmboot block of the FPGA is reading to load the different sections. The second, then just after that, you have the boot stub, which is this very simple configuration that is just the FPGA image. After that, you have an empty space, which theoretically could contain software for the boot stub, but we don't have a microcontroller here. It's just logic, so we don't use that block. Then we have the DFU FPGA image, which is the configuration that contains a RISC-V microcontroller and the software that is just after that here. This is the software for the RISC-V microcontroller that implements USB, with which we can then program the flash chip with. And we can flash either app1 or app2. In these sections, we can put in our own bitstream and our own software if we decide that our design should contain a microcontroller or not. This is something you can decide. You don't have to put a microcontroller in there. You can just do pure logic. It's like if A is on and B is on, C is off, let's say. It's like you can just do that, or you can configure your FPGA to become a microcontroller. So yeah, that's the logic here. So let me answer this very good question that Reset Public is asking. What is the advantage, disadvantage between FTDI chip, not FTDI chip? So there's a lot of factors here. One is the FTDI chip can run at high-speed USB speeds. Our bootloader is only full speed, which is quite a speed difference. Second, the FTDI chip is supported by the vendor tools. The DFU bootloader programming thing, you would need to use your own DFU bootloader. It's not a big deal really, but it's not directly compatible with the normal flow of the vendor programming tools. It's like, arguably, it's like people don't love the programmer, the Radiant programmer. It's quite a janky programmer, but it is there, and people are using it on Windows, and it has a UI, and you can click Ubuntu it together. So this is something that you don't have with here. You would need to use a DFU programmer for this. 3, what else? So if you want to communicate with your computer after you program the bitstream, you would have to put the USB stack into the FPGA, which will occupy space in your fabric. If you use just the SPI interface, the SPI implementation is much, much smaller than a USB implementation would be. So just using an FTDI chip with SPI uses much less of your FPGA resources than having to put the whole USB stack in the part. On the other hand, you could always take an external FTDI adapter breakout board and just connect it to get SPI, but you don't have it out of the box. So it is a disadvantage here. What else? I'm sure there are a few other like disadvantages and advantages. The advantage here, it's like doesn't require a chip. It saves a lot of money. So it's not just a few dollars. It's essentially not having the FTDI chip cuts the BOM cost by half, pretty much. Not having the FTDI chip. So it's like, this is how bad it is with the FTDI chip. I am sure that I have the feeling that Lattice has the way of talking to FTDI and getting much better prices than I can as a small designer and small company. So yeah. This will be cool. We have some other plans to replace the FTDI chip on the full Icebreaker with a microcontroller. So there are plans that, but it's like there's a lot of engineering involved because we have to re-implement a lot of functionality. There's already existing firmware for it. Long story. Other stream, not today. We will talk about what we will do with the full-size Icebreaker, how we will get rid of the FTDI chip on there. This is something also planned. We will be working on that. But for now, we are stuck at least on the full-size Icebreaker with the FTDI chip. Tiny FPGA must be reset to upload a new. Yes, you have to. Yes, you have to. The bitsy, you have to unplug it and plug it in again. With the FTDI chip, you can just keep it plugged in and it will reset everything and it will work. On the other hand, I'm pretty sure if you put a USB stack anyways on your FPGA design, then you can give a DFU stub, so-called, just like on a microcontroller, and allow the computer to reset and restart into the DFU bootloader. This is something we should probably explore to provide some block for people to use that you can just drop into your own design. Yes, it will occupy a bunch of space, but if you have a RISC-V microcontroller on there anyways, this shouldn't take too much resources because you then have the USB. You have USB and a RISC-V that you are programming anyway. So this might be a good reference design for someone to put together and allow to the DFU bootloader, or DFU util already does try to connect to a device, and if it sees a DFU stub, it has a mechanic where it restarts into the DFU bootloader. Perfect. So Sylvain already thought about this and it's all solved. It's all done. Yes. Great. Awesome. Wonderful. So yeah, I am now speaking of from a not fully up-to-date spot. Sweet. Awesome. Great to hear that. Jordi, thank you very much for Twitch Prime to Tier 1 sub. Thank you so much. That's, as far as I understand, that's an upgrade. I'm still learning about this Twitch thing and all those different tiers. Awesome. Thank you so much. Okay. Yeah, but you don't lose the design here. So in case of the of this bootloader, you actually are uploading the design into the flash chip. So you are this will stay on there. The user application will stay on there. It is not just once and then you have to after repower you lose the configuration. So this might be an improvement on top of the Tiny FPGA, how this bootloader was working on the Tiny FPGA, because you are configuring directly the FPGA probably. Anyways, I don't exactly remember what the mechanic was on here. But yeah, with the bitsy and the bootloader from Sylvain, you don't lose configuration when you repower the FPGA. You don't lose the configuration that you as a user programmed in. So that's good. All right. So that said, little bit more of a story what happened yesterday. I was trying to get these tools put together, so everything seemed to work at first. Then I could not get the bitsy to start up, and then I started to look into let me how do I frame this whole story? So what happened essentially is my Ice40 toolchain that I had installed had a bug that got fixed eventually. And when I tried to rebuild the toolchain to get rid of the bug that was in there, the newest version has a regression in a very specific place that causes issues synthesizing the hardware that we have here. So it fails to synthesize. So I had to roll back one revision earlier until the regression is fixed upstream. So it was figuring out what was actually going on and why it was breaking. And because I didn't build the bitstream, so I didn't know what I'm looking at, and Sylvain did the work. Essentially, it was a back and forth between him and Greg DeVille to figure out when, where, what actually was broken and what the actual issue was. Am I doing something wrong? Am I putting something? Yeah, so there was a colon missing in one of the commands. So I think what we should do is make a script inside your system that actually runs all the steps and puts it together correctly with just one command run, without me having to go into 4 directories and build several things and then put them together into one bitstream. That is probably the safest thing, so then we don't introduce issues there. It's pretty simple. It's like a 3-liner, essentially, shell script, or makefile or whatever. The interesting thing is, because it consists of several parts, it makes sense to keep it apart, especially when you do development, because most of the time you are just replacing one part of it. It's like you just want to reprogram the program for the RISC-V chip, or you just want to reprogram the bitstream for the USB bootloader or whatever. But this like one blob multi-boot binary that I was trying to build, I didn't know if I'm doing everything right. So, and then I ran into toolchain issues. So that took the whole day yesterday. That's why I am a little bit late today, because I wanted to figure it out. But now I have a working configuration on the Icebreaker bitsy. We were also debugging it on the full-size Icebreaker. So the cool thing is, like, it actually uses the RGB LED on here. Let me just show you. This looks really cool. So it's pulsating the RGB LED really nicely. So that's the bootloader running. But yeah, if I wanted to run the same bootloader, I need to essentially connect a USB cable to some of the GPIOs on here, and then connect that to the computer, because this is FTDI programming the flash chip. And oh, Nettie, thank you so much for 100 RGBs. 100 blinky RGB LEDs. Thank you so much. Anyway, so yeah, that's that, and then we have this guy. And so, where were we? We should try to program this guy with some bitstream, probably. That would be one thing to do, to try that out. Just some simple bitstream as an example. because did I still want to show anything else on here regarding the design? I think I did have a... Oh yeah, the FOMU toolchain has a broken... has a bug. Yeah. So essentially the lesson we learned here, we really need nightly builds that are automatically built of the binary, so it is easy to jump to an older version of the toolchain. We really need that, and there's several people working on that. I know that Miodrag Milanovic, I think that's his name, he started working on that, and I know that I think Ed Borden, wanted to work on that. So we will get a CI nightly build system sooner or later. So I'm really looking forward to that. That will definitely improve our life. Yeah, well, this is a good thing. So Sylvain is like, you says he he breaks stuff with his, but this is good. You're pushing the envelope of what the tools do. This is how we find the issues, and this is really wonderful. I see this whole tool chain just progress so quickly forward and improve so nicely. I'm not mad at all about these issues that we ran into. I think it is exciting, and especially considering that this process leads us to learn more and actually find out things and fix things and improve things, and in a general as a process is really nice. And it's essentially we just need more and more people that are involved and put their precious time into making things even better. It's like the CI stuff is just, to be honest, it's very boring to implement, but it will make the development so much nicer for so many people and have access to older binaries. And yes, I also build head of all the tools using the Summon FPGA tools, which is my project here, which you can find. Esden and Summon FPGA tools. So this is a script that I started, and people contributed some patches to. And it ended up being pretty easy to build the older version of the toolchain. It just takes time because especially my streaming machine is not a very fast computer, which I would love to fix. Yeah, it's if I had the binaries, I could just download them and then get going. But the majority of time took us to figure out what the actual issue is and what solves it. It's like we had to make a lot of tests where I sent bin files to Sylvain, and he was putting them together, seeing, oh, it doesn't work for me, but the ones that I built, they work fine. So I started to question my sanity. It's like, am I doing something wrong? Am I just do I have bad karma or something, and the computer hates me? And so this is how it worked out, and then eventually we figured it out. And this is what is wonderful. This community is so helpful, and we all work together and help each other. It's like Dave Shah just jumped in and was like, who is the guru of the toolchain, and he's like, wait a second, I will look into this. And he within an hour circled in what the actual bug in the toolchain was and created an issue. And Claire is assigned it to herself during when I was asleep, and it's like was working on fixing the bug so that it is completely gone. So it's really nice to see the process and be part of it. It's seriously, I love being part of this community and being part of open source. You see how the sausage is made, but you also can contribute to make the sausage higher quality, which is nice. Yeah, Harman support, yeah. Cool, cool. Yeah, nice, Twonsky. Okay, so what was else? I think we should try to program this thing with some bitstream. I think that would be a fun thing to do on this stream. Now that I told you this whole story, oh yeah, right, the toolchain. So building the toolchain. So this is all I needed to do. I hope you can see this. So summon FPGA tools. There are environment variables that or parameters that you can set. So I just had to know which Git revision I had to roll back to, and I just provided it here and rebuilt the toolchain, and I have a working toolchain. So it wasn't a big deal at the end. And I tend to build it myself anyway, so I usually don't rely on external binaries. But yeah, as I said, now I'm starting to repeat myself. It would be nice to have the pre-built nightly builds. Just saying. So if you want to help out, Ed or help out Mildrak and jump in, and you have experience with building CI systems, I'm sure there's always something interesting to do and to help out. You don't have to be an FPGA guru to help out with this effort. Definitely not. All right. So let's see. Icebreaker examples. So let's see if we can just flash an example, which is, for example, the PDM fade gamma, which is let me show you what it does. So this is a design which is just logic, which maybe I should start with something simpler than that. Maybe let's start with the PWM first. PWM fade. So this is a repository that you can find in Icebreaker. It's called Icebreaker in the repository here. So GitHub, Icebreaker. This is the Icebreaker organization on GitHub. There we go. Icebreaker examples. And this is Verilog examples that we have, a bunch. I do want to add more and expand this. I didn't have much time to add more. If you have nice, simple examples you want to add to this repository, they are always welcome. And please do. If you find something interesting that we should have in here, please do. We also have example repositories for NMigen examples for Icebreaker. We have Migen examples somewhere here, Migen examples. We have iStudio examples. So this is the graphical programming UI. We have the What the Fuck PGA workshop, which is the predecessor to the Icebreaker workshop. So this is the newest version of the workshop to get started. And then we have Icebreaker LiteX examples, which is here. This is an actual RISC-V core example that you can program in C or Rust and eventually also Python. So yeah, we will just, this is the simplest thing, is the Icebreaker examples, which is just pure Verilog, and it's just a make file, and it is very simple. And we have this PWM example in here, which will take the two LEDs, which is a red and green one on the board, and use PWM to fade them in and out. So I just created a PWM counter and compare. So there is a compare register, and there I have some synchronous logic. It's like, this is very simple stuff. There are probably better, cleaner ways of implementing things, so take it with a grain of salt. A lot of these examples are my learning experience examples where I learn how to implement things. So essentially, if the PWM counter equals compare, so equals the value in the compare register, then the PWM will be 1, and if it is otherwise, so it is greater equal the value in the compare register, then it will be 0. So basically, it counts and it's on, counting until it reaches the count value and drops and counts to the end, and then starts again when the counter rolls over. So it basically wraps around. And so you have a counter, counts, goes down, counts, goes up again, and so on. And here I have a loop where I have a divider, and this is an increment counter and a compare value. So every time the increment counter reaches the compare value, so basically you create a counter like on the microcontroller that counts to a value and resets, counts to a value and resets, counts to a value and resets. So so if the PWM inc counter, and this we are using the overflow bit to basically do an action, to have like a strobe. And so if the PWM counter's bit 17 is set, then PWM value is set to PWM value plus 1, and the inc counter is set to 0. And so essentially we are incrementing the compare value in the hardware that is here above, and we are resetting our counter to 0. And if the PWM compare value -7, what is going on in here? Oh, right. This is a different thing. So this is creating an up-down counter. So I implement a way of going up and down in here. And so if the compare value 60 minus 7, so how does that work? I don't remember. Compare value. Oh. Right. I negate. So basically, so what I do is I take the value, the PWM compare value that is always going up, and taking one of the high significant bits and basically bend it backwards so that it counts up and then counts down in the resulting value. So essentially I negate the bits that would be counting up and negate them down to create a down counter. So that's what we are doing here. And with that, let's synthesize this. Let's show you how documentation. There is comments in here. I just was reading directly the Verilog. I have comments in there that should be explaining it, but yeah. So this is synthesizing this, and done. 3.5 seconds on this slow machine. It's pretty good. All right, so now we have a bin file. Now let's see. DFU util. We should list devices. We have one DFU device that I cannot open, so I have to do it as root because I would have to add it into the plug dev, change the permissions on that, but I will not do that. So I think Sylvain said I do DFU util A for this should be the first application for a alt 0, and then let's see, read firmware from device into file. And then where is the right? Download. D, download firmware from file into device. And then -E you say for detach. So it should detach afterwards. There we go. Okay, so let's see. Let's zoom in on this guy so that we can see what's going on here. So this is fading nicely, and it should be available as, let me make this bigger for now, just for a moment. Let's try it. No. Oh, yeah, I have to do it as sudo. Wow. Sudo. Is it working? It's not working. Did it start? It did flash. It did flash something. Let's see if I have to repower it or something. Nope. No, it's not. I definitely can get it back into the bootloader. No, that's not good. Okay, so it did restart. Anyway, so how this should look like, let me show you on the full Icebreaker. Let's use this guy. This is how the PWM thing should look on the red and green LEDs. Programming, reading. So this is how these would look like. They would just fade in and out. Is that visible even? I think I should. There we go. There we go. That should be better. A little bit more contrast for the. There we go. There we go. Come on. Why is it? You can get some focus on this. There we go. So you will see that how they. All right. So now let's go back. Let's do some live debugging. So first of all, let's get it into DFU, holding button, plugging in, then it reboots. So it went from, so this is how it looks like. I plug it in, it shows a red LED. You see that there's an RGB LED in here. Oh, apropos RGB LED, one more story here. I actually, let's see if I can just move myself here. Let's reorganize the scene live here. So what happened is it turns out we actually got the rotation of the RGB LED wrong after all. After all me trying around, I actually swapped in my head cathode and anode, and I used it in the wrong way around. So I had to heat up the LED and like with tweezers poke it, and then it rotated and resoldered in the right orientation. So now the RGB LEDs are working. So let's see. So that should start. Berg PB, thank you very much for the follow. Welcome to the stream. If I see it correctly here. Yes, thank you. Okay, so DFU util. Yeah, so let's do sudo. Oh, RISC-V firmware. Alt0, the bitstream. Yes, that looks correct. Yeah, so essentially this seems like it is correct now, at least to me. Yeah, that looks fine. Try without the E, so A0, and then let's try it again. A0 and then D, right? And then minus E, PWM bin. We are using the bin file, right? Okay, so let's try it again. Download. Oh, now it is downloading. Now it is doing it. I'm not sure it did that before. And now I can press the button and then it will start into the application. Yeah, there we go. Perfect. So it works. Yay! Celebrate! Sparkles! Yeah, that's the first time I programmed an application using the bootloader. Just FYI, it works. Woohoo! So that's cool. I don't know what happened the last time I tried it. Let's see. What was the error that we got? It was something, yeah, it just said determining device state, and it was DFU idle, status 0, continuing. So yeah, we might need to do some little... so bootloaders in general, it's like, it works, when you write it, it works for you, and then it's... The more people bang on it, the more you find some weird corner casing, especially because it's USB. USB is so fun. And so everyone's controller is different, drivers and different PCs, different ports. Like, for example, I can't currently use this FTDI programmer. That's a separate story. So I made this this programmer, which is like a FTDI programmer multi-tool. I should actually show you maybe here. So I made this. This is cool, but the problem is, for some reason, my streaming computer decided that it will not enumerate it anymore. It's like, oh no, I'm above it. Not anymore. So it does enumerate on one of the USB 3.0 ports on my streaming laptop. And that one I use for one of the camera streams, so I can't use it during the stream for this kind of stuff. And it does enumerate fine on my normal daily driver laptop as well as on my desktop computer. So there you go. Wonderful, right? So we can try it again. We can actually reprogram it again with the PWM tool. Let's pull this out again. And we hold the button and plug it in again. This will get it into the DFU mode again. So you see the fading RGB LED. I think I'm too close. That's the problem here. Sorry about that. Now it should focus. Now it focuses properly. Good. So that will work. And now, if we do list, DFU list, it should still pop up. Yes. And now, when I do this, let's try the -E again. Just one more time. No, that fails. Yeah, I know this just restarted, but it's still not right. Because it didn't program it. Yeah, the -E somehow doesn't work. Weird. Do I have to put the -E earlier in there? So that it does it in the different order? That's weird. So I can't use the -E. I am being pinged somewhere here. Let's see what's happening. Ooh. That's fine. minus R. So let's see. So let's see DFU util. What are the options? Minus R is reset. So what order of operations should it be? Minus big R minus E? In that order? So let's see. Oh, it's not available anymore now? What? Why? No. What? No E. Okay. So I will remove that. Okay. Let's try it again. Now it's programming. Yes, as expected. Programming. And reset. Okay, cool. So that was the correct incantation. All right, so the correct incantation is DFU util minus A0 minus D pwm.bin minus big R. Yes, I think minus E was detaching it. That's what was happening. And R is the reset to get into the programmed application. So cool. Yeah. Anyways, so that's very exciting. We can play with some few more things, but what I wanted to get to also is, so we have the one more thing that is a difference from the Icebreaker, is the fact that we are using is that visible? Maybe I should crank it up again here. Come on. Can you please give me some brightness? Thank you. So, the Icebreaker bitsy also has an SPRAM chip in the back. So this is a difference from the Icebreaker bitsy, Icebreaker, the full-size Icebreaker. You can get the RAM chip on here by soldering it piggyback onto the flash chip, and not on this board, but the newer revision boards have this pad on the side. See this pad? You basically, this is the chip select of the other chip that you can solder to that pad. Like basically have a leg sitting very fancifully to the pad on the side. So it's like the pinky finger on drinking your tea. That's what you will do with the chip, with the SPRAM chip. You piggyback it on top and then fancy pinky the chip select to the pad on the side. It's a little bit of finicky because the SPRAM chips are smaller than the flash chips, so you have to bridge it a little bit. I will still do that for reasons like for testing, especially considering that Sylvain, in his marvelous capabilities, managed to get SPRAM running at really high clock rates. It's like you tell me what it was, but it was impressive. You can run. There's HDMI 147 megahertz. It's just insane. So this for this FPGA to be able to do anything at these speeds is just very impressive. So well done, Sylvain. You guys should applaud him very much, because that's wizardry. And so with the SPRAM chips, we can now have additional external memory. And besides the internal BRAM that we have, we can also... Crooks, thank you for your follow. Welcome to the stream. Yeah, so we can now also run applications from RAM using the SPI quad SPI interface. And he got 1080p 60 megahertz pixel clock. Oh, it's the same as the clock for the 1080p 60. Oh God. So you know that we have these HDMI PMODs. So this was the first thing that I think Sylvain blew my mind with, is that it is possible to do 1080p video out of the Icebreaker. Seriously, what the hell? That's amazing. So, and it's also 60 FPS, right? So, wow. And so we can use the SPRAM to actually get data for the HDMI output out of there. It's I think it is a smaller color resolution or something, but still, if we can put a frame buffer for the for at least certain video qualities for the HDMI output, that's just intense. So that is really useful. That's why I put the footprint on the back of the Icebreaker bitsy so that it is easier to put on. I still thought it was a user choice. I will be redoing this board to put everything on top, so all the Icebreaker bitsys will come with SPRAM. Exciting new projects on the horizon. I'm excited. It will be great. We will continue working on different things. So I think the next stream will be, I will be showing off a LED cube. So you might or might not know, in some of the previous streams I was showing you the LED cube that we built together with Bob Miller, who designed the 3D printing insides, and Sylvain wrote a lot of the gateware for the LED panels. And that cube was inspired by a cube from Germany. They are two guys, now one, that design a very fancy, very nice cube. It's the Dot, and it's square. They are called Square Wave. If I can find the page, Square Wave Dot. So that's their GitHub page, and yeah, there we go. So that's the website. So this is Hannes, who is also here in the chat, he sent me one of the cubes here so that I can play with it, and I will be helping them with the electronics design for the future revision, and then eventually a crowdfunding campaign for this, hopefully. And I would like to show it off. Oh yeah, happy teddy bear, there he is. That's Hannes. And so we are currently looking for software people that want to get involved in the project to help out with yeah, JPEG loading. Yeah. This project is quite involved and quite complicated, and it is all just by the straps. It's like we are putting our time pretty much for free into the project. And we are looking for some people that might be motivated to work on something like this. For example, a problem that we are running into is so the history is the following. It's the cube inspired us to build our cube using the Icebreaker, and then eventually the Icebreaker design went back into the cube to drive the LED panels and uses Sylvain's bitstream. But it is connected to the Raspberry Pi that runs the show over SPI instead of USB. And it turns out that driving high-speed SPI on a Raspberry Pi is not as simple as one would think. So we need to do some Linux kernel development to make a driver with a frame buffer to make it efficient and not lock up the whole system and cause issues. So we are looking for someone who is interested in poking around in the Linux kernel to write a proper driver for this. And then eventually we can hopefully make it into a nice campaign thing. And there's way more other software that needs to be written. There is a simulator for this that is essentially simulating in 3D the cube, so you can make animations. The framework is written in C++. So if you are bored, you want to learn something new, you want to play with LED cubes, give us a shout out. We are looking for someone. Otherwise, I think I will show the cube off and the current state of affairs on the next stream, probably next Tuesday, with the schedule that we are currently having. And yeah, so that would be the wrap for today. And we are ending a little bit earlier than usual, but that's all right. Things sometimes take longer, sometimes we wrap up faster. And this way, I again thank you for the Twitch subscribers. Thank you very much to all the Patreons, and I want to give the special shout outs to some of the Patreons that are in the shoutout tier, which is thank you very much to Jamin, Brennan Ashton, Drew Fustini, Edward Borden, Go Jimmy Pie, Jeff Wang, Jordi Parky Rodriguez, Kelly, Micah Benovets, Sid Price, and Tom Keddy. Thank you very much. I appreciate you all. And as always, if you have been, thank you for watching. Bye.